Today, we are going to integrate some rational functions. Probably given the time, integrate a rational function, but let's see how far we get. Let's review the rules or the things that we need to remember when we're integrating rational functions. First, we want the degree of the numerator to be less than that of the denominator. So if the degree of the numerator is greater than or equal to that of the denominator, then we're going to use long division to break off a polynomial and then a rational function where the degree of the numerator will be less than that of the denominator. We'll go from an improper fraction to a mixed number. That's what long division is going to get us with the polynomials. Number two thing to check out, if the denominator is quadratic with complex zeros, then you'll get a combination of arctangents and natural logarithms. Arctangents come from a constant over a squared plus x squared. Natural logarithms come from an x over a squared plus x squared. A squared plus x squared being the generic quadratic with complex zeros. The addendum to this, if your quadratic with complex zeros has an x term, then you're going to want to complete the square. So it looks like a squared plus a squared. I just realized I used a here and I used a in my general description. So part three, the new thing that we're learning about is partial fraction decomposition. This is what we use if q is quadratic with real zeros. We did an example last time where the degree of q was equal to 2 and there were 2 real zeros. We want to split the fraction up to get a pair of natural logarithms after we integrate. Or if the degree is greater than 2, then we're going to use partial fraction decomposition. A polynomial can always be factored into a product of linear factors for all the real zeros and quadratic factors with complex zeros for all the complex zeros. Because if we start with a function that has real coefficients, our complex factors will come in conjugate pairs, a plus or minus bi. So with all this in mind, let's take a look at this example. We've got an 8x squared minus 11x plus 29 for a numerator. And we got x cubed minus 2x squared plus 9x minus 18 for a denominator. Let's think about all the things that we need to notice. We notice that the numerator is of degree less than the denominator. The degree of the numerator is less than the denominator already, so we don't need to use long division. That's the first thing we notice. The degree of P is 2, and the degree of Q is 3, so no need for a long division. Yay. So we don't need to use long division because the degree of the numerator is already less than that of the denominator. We do notice that the degree of Q is 3. So the degree of Q is greater than 2. So we will have to use partial fraction decomposition after we factor the denominator. So the degree of Q is equal to 3. So we will need partial fraction decomposition. Boo. Fortunately for our heroes, so what that means is we're going to need to factor the denominator. This x cubed, we're going to need to figure out what the linear factor is and what the quadratic factor is, because the quadratic factor might be quadratic with complex zeros, or it might be quadratic with real zeros. But we need to start factoring it. We know, since it's cubic, that there will be a real factor, or sorry, a real zero. So this means we need to factor. Since we're doing partial fraction decomposition, that means we need to factor the denominator. So fortunately for our heroes, if you look at the 4 terms, I've got an x cubed minus 2x squared, then I got a 9x minus 18. So I have an x minus 2 and an x minus 2 as a common factor. I picked this one because I can easily factor it. So note that the denominator is factorable by grouping. There's a common factor of x minus 2. So if I factor an x squared just out of the first two terms, that leaves an x minus 2, and then the 9 and the 18 means we could factor a plus 9. That leaves another x minus 2. So the denominator is factorable. It has a factor of x minus 2 and an x squared plus 9. There's the factored denominator. I chose this particular polynomial because I knew that that would happen. Because what I wanted was a linear factor, and I wanted a quadratic factor with complex zeros. So x squared minus 9 has plus or minus 3i as the zeros. Now, we're going to use partial fraction decomposition to make one term with a denominator of x minus 2 and another term with a denominator of x squared plus 9. So I'm going to break apart the partial fraction decomposition portion of events. So we have 8x squared minus 11x plus 29 over x minus 2 times x squared plus 9. And I need to write this into two terms. One term has a denominator of x minus 2, and the second term will have a denominator of x squared plus 9. Above my linear factors, if I keep in mind, if we're coming at this from a calculus perspective, we know that the numerators of the linear factors have to be at most, or have to be one less than the denominator. So I'm going to put a generic constant over the x minus 2, but the quadratic with complex zeros gets a linear factor on top. It's going to have some form of bx plus c. We're further going to split this by distributing the x squared plus 9. Have a bx over x squared plus 9. That's going to give us a b over 2, natural log of x squared plus 9. And then there will also be a c over x squared plus 9, which will be a c over 3, arctangent of x over 3. So just thinking of the calculus portion in the future while we're doing the algebra portion right now. The technique for partial fraction decomposition is to figure out what your decomposition, you want your decomposition to look like, and then put it together to match what you started with. So this is going to be an a times x squared plus 9 plus bx plus c times x minus 2 over the common denominator of x minus 2 times x squared plus 9. For those of you following the path of the I'll plug stuff in, and you see that you're going to plug in a 2 to wipe out this term, you got to figure out what to plug in here. You're just not going to be able to zero out this term. So just pick two values, pick x as 0 and plug that in to see what the other, to find the b and c. You're going to need to plug in 3 values because you're looking for a, b, and c. So for those of you following the shortcuts, plug stuff in path, 2 is a good choice to plug in, but the x squared plus 9 doesn't naturally lead to anything that makes it easy to plug in. So just plug in 0, that takes care of this. And then plug in 1, and then you'll be able to get at the rest of them. For those of you who want to continue on the path of, I'm multiplying this out so I can equate coefficients, let's keep going on that in that one. So I'm going to multiply out the numerator, and that's going to be an ax squared plus 9a, ax squared plus 9a, plus, and then I have to multiply bx plus c times x minus 2. So I'm going to have bx squared minus 2bx plus cx minus 2c. Now I'm going to gather the like terms to find out my coefficient of x squared. So let's see what we got. I'm going to have enough room. I don't have enough room. The x squared terms, there's an a and a b. So I have a plus b times x squared. My x terms are a minus 2b and a plus c. So plus minus 2b plus c times x. And my constant is 9a minus 2c. And my denominator is still x minus 2 times x squared plus 9. This is the partial fraction decomposition technique. The first thing is knowing how the decomposition should look. The second thing is just putting your decomposition together and making it look like what you started with. So what we started with was 8x squared minus 11x plus 29. Now, at this point, if you're wondering if Wolfram alpha can do your partial fraction decomposition, it totally can. It can also do your factoring. But if you're going to bring Wolfram alpha to the table, just use Wolfram alpha to integrate the function. I mean, if you're going to bring technology to bear on a problem, bring technology to the problem. We're training here. I mean, having Wolfram alpha do the integration for you, or even just a part of the integration for you, that'd be like going, that's skipping leg day. Or worse, skipping leg day entirely and then watching upper body on a video. And it's like, oh, whoo, I'm really tired because I watched somebody else work out. So now we're going to equate coefficients. A plus b is equal to 8. So now we're going to equate coefficients to get a linear system. And we're going to have to do this on the next page. So we've got a plus b is equal to 8. A plus b, space for c, is equal to 8. I've got minus 2b plus c is equal to a negative 11. And I've got 9a minus 2c is equal to 29. So now we can start adding these equations together to eliminate variables and solve the system. I suppose we could grab our, if the only tool that we have available to us is the TI-89 or TI-84, since it doesn't do integration and it doesn't do partial fraction decomposition, we might be stuck solving the linear system on the TI-84. So that's certainly a possibility. All of a sudden, it doesn't look like the one that I did earlier, but that's okay. Press on anyway. I'm going to multiply the first equation by 2 because my plan is to eliminate the b's to get an equation in a and c, and then combine that AC equation with the third equation and eliminate whatever is most convenient. So I'm going to combine these two equations. I'm going to say 2a plus 2b is equal to 16, and minus 2b plus c is equal to negative 11 to come up with a new equation in a and c. 2a plus c is equal to 5. And this one I will combine with the 9a minus 2c equals 29. And I'll multiply this 2a plus c, I'll multiply that one by 2 again, so I can eliminate the c and find out what a is. So now I'll multiply this one by 2. So 4a plus 2c is equal to 10, and 9a minus 2c is equal to 29. Now I think something went wrong. Can I drop a negative somewhere? (8x squared minus 11x plus 29). That's what I wanted. (ax squared plus 9a plus bx squared minus 2bx plus cx minus 2c. So I got ax squared plus bx squared. So a plus b is the x squared. I've got minus 2bx plus c minus 2b plus c times x, and that's negative 11. And I've got the 9a minus 2c is the 29. So why am I getting, oh, 4, 9 is 13, God. Man, I don't know what's wrong with your teacher. 4, 9 is 13, not 12. So 13a is equal to 39. And so a is equal to 3. All right, this is why, by the way, why we use machines to do this kind of stuff. So a is equal to 3. Now we're going to just kind of go backwards through the stuff that we had. So if a is equal to 3, then I could put that into, let's say, this equation, 2a plus c is equal to 5. So now I'm just going to go back through the rest of it. So 2 times 3 plus c is equal to 5. So c is equal to negative 1. And then I can just take the c, combine it with, or I could just use the a, and the b is equal to 8. And I could say that 3 plus b is equal to 8. So b is equal to 5. Whatever happens to be most convenient. So now we have found a, b, and c. We have completed the partial fraction decomposition. So let's go back and remind ourselves what we were trying to integrate in the first place. So when we want to integrate 8x squared minus 11x plus 29 over the x minus 2 times x squared plus 9 to x. We actually can integrate, now I got to remember which one is which. I set it up as a over x minus 2, so 3 over x minus 2 plus 5x minus 1 over x squared plus 9 dx. There's the partial fraction decomposition of my original rational function. In this case, since I have an x squared plus 9, I can break the 5x on top and then a 1 on top. So I'm actually going to break that into 2 terms. So what we're integrating is 3 over x minus 2 plus 5x over x squared plus 9 minus 1 over x squared plus 9 to x. And now we can finally do some calculus. The integral of 3 over x minus 2 is going to be 3 natural log of the absolute value of x minus 2. The integral of 5x over x squared plus 9 is going to be 5 over 2 natural log of x squared plus 9. And the integral of 1 over x squared plus 9 is a minus 1/3 arctangent of x over 3 plus c. And this is why we love integration so much, because that was fun. I stopped using 9. My 9s are really weird looking. Any questions? Can't you see how important this is going to be in your future when you're in charge of the SpaceX mission to Europa. I don't know if that happens in your lifetime. That'd be really cool if it does, though. Maybe the mission to Mars. I think one of the reasons that we haven't like flown people to Mars is that it doesn't seem like there's anybody there to beat up. And we don't think there's anything on Mars that would make it worth the trip. Because just like knowing stuff is just, it's not. Accomplishing things, nah, that's not important. Got to find a way to make money. So the reason that whenever we integrate our way into natural logs, we should use absolute values. I didn't need the absolute values on the natural log of x squared plus 9 because x squared plus 9 for real inputs of x is always positive. So I just didn't bother with the absolute values. That would have seemed excessive. You could put them in there, but if you want to make sure that you look like you're paying attention, you want parentheses. In the 5 is just from the numerator is a 5. The 1/2 comes from a substitution. The substitution that we made here is to say w equals x squared plus 9. And so that dw is 2x dx. And so a 1/2 dw is x dx. So that's just going way back to our substitution days. How's everybody okay?
Professor, what was the part that you were talking about, just plugging stuff in?
What do you mean plugging stuff in?
Oh, you were saying, for those of you that are just going the route of plugging things in and eliminating.
The shortcut, yeah.
Yeah.
So yeah, I use the word shortcut in that sentence, which is the word that we really want to focus on. It's like, well, this seems too long. What's the shortcut to this? So if we go back to this, this original equation up here, we've got, if we just ignore the denominators and focus on the numerators, because that's what we're trying to equate. So let's talk about the shortcut. I was planning on talking about the I'm not making fun. I was planning on talking about the shortcut anyway.
Okay,
so,
thank you.
We're trying to solve this for all the x's. Let's talk about the shortcut though. So let's talk about the shortcut for where you plug in some values for x. So we isolate the numerators. We're just going to look at the numerator, and we have 8x squared minus 11x plus 29 is equal to, and I'm just going to look at the one where I haven't multiplied things out yet. A times x squared plus 9 plus bx plus c times x minus 2. So we're trying to find a, b, and c that make this true for all the values of x, except of course for x equals 2, because that would make our denominator 0, and we can't have that. But we're totally going to cheat, because if we just look at the numerators and pretend that the denominators aren't there, I'm going to pick a value for x. I'm going to choose x to be 2. So I'm going to say x equals 2. And when I say let x equal 2, you say, are you sure that that's okay? And I'm like, oh, don't worry, I'm a professional. You can actually try this one at home. And we're just going to plug in 2 because it's going to eliminate this, and only thing that's we're looking for that's left is going to be the a. So I plug in 2, I got 8 times 2 squared minus 11 times 2 plus 29 is equal to a times 2 squared plus 9 plus b times 2 plus c times our favorite 2 minus 2. So what this does for us is it takes 2 of the things that we're looking for out of the equation. We do have to sort all this out. We get 2 squared is 4 plus 9 is 13a. And then we have to simplify this side, so it's going to be 39. I'm really fast at arithmetic. Let me finish that sentence. I'm really fast at arithmetic when I know what the answer is going to be. And so this gives us a is equal to 3. Now, so by choosing a very convenient value of 2, it wipes out 2 of the things that we're looking for. It takes out the factor with 2 of the things that we're looking for. Now we still need to find B and C. We don't have the linear system to appeal to because we're trying to shortcut the linear system. I don't know why linear systems are so cool, but some of you are like, oh, nah, I'm not into those linear systems. So I'm just going to pick another value for x that is going to be convenient. And I'm going to keep in mind that a is equal to 3 now. So I'm just going to pick another value for x that'll be convenient. That'll take one of these a, b, or I'm going to pick x equals 0. That'll take out this b, and that'll just leave c in the equation. So that's my next choice. So now I'm going to come along and I'm going to say, let's let x equal 0. So 8 times 0 squared minus 11 times 0. Oh, we love plugging in 0, don't we? We now know that a is equal to 3, so that can go in. And then I have 0 squared plus 9 plus b times 0, takes out the b, plus c times 0 minus 2. So over on the left, I get just 29 this time. And over here, I got 3 times 9 is 27. And I have minus 2 times c. So now I know a and I know c, and I chose a value for x that would conveniently get rid of the b. And so I can solve for c. C is -1. Then I've got to solve for b. I don't really have a convenient value, but I have a and c already, so I can pick anything else. So I'm going to go ahead and pick anything else. I'm going to pick let x equal. I didn't have a convenient choice for this last x, so I just need to pick anything I want. So I'm going to have 8 times 1 squared minus 11 times 1 plus 29 is, I know what a is 3. So 3 times 1 squared plus 9 plus, I know what I know what c is now, so b times 1, and I know c is -1, so it's -1. But then I have 1 minus 2. So over on the left, I get whatever I get. So I get 29 minus 11 is 18 plus 8 is 26. Over here, I get 3 times 10 is 30. And I have minus 2b. And, oh, sorry, minus 1b. Yeah, 1 minus 2 is -1 still, right? I haven't checked up the numbers today, so hopefully 1 minus 2 is still -1. So -1 times b is -1b, and -1 times -1 is +1. So here we can solve for b, and we get 5. So now we have a, c, b, and c, and we got that just by plugging in convenient values of x that take out the things that we're looking for. So that's the shortcut to the linear system. Specifically, it shortcuts the linear system. Make sure I don't smear anything. So that's the shortcut to getting around the linear system.
Professor, I have a quick question. So
Yeah.
where you're inputting 2 for, I'm sorry, B times 2 plus C, that just gets rid of it so that we can just work with A?
Yes.
Okay.
Yeah, by choosing x equals 2, since the bx plus c is being multiplied by x minus 2, when x is 2, bx plus c gets multiplied by 0. And so that's why this whole term drops out, because the 2 minus 2 is the 0. And that's what takes out this whole term.
Gotcha. Thank you. That's much better.
Yeah, because you get around solving a linear system. So it's a shortcut. But it's a convenient shortcut. Can't always solve linear systems like this, but when the linear system comes from this polynomial business, it's actually more convenient to do this. So for comparison, once again, if you're going to bring technology to bear on a problem like Wolfram Alpha, don't bother using Wolfram Alpha to solve the linear system. First of all, it's not really that good at solving linear systems. It takes too long to input. And second of all, if you're going to use Wolfram Alpha, just use Wolfram Alpha right from the beginning. So, no, I didn't input Wolfram Alpha. Go ahead and just input your original integral. You don't even have to put the integral. You just have to put the rational function you're trying to integrate into Wolfram Alpha. And one of the outputs will be the antiderivative or the indefinite integral. So, but if the only technology you have is a TI-84 and the TI-84 does not do indefinite integrals for you symbolically, and it does not do partial fraction decomposition for you, you can use a calculator to solve the system, and you should know how to do that. So if the system we have is this a plus b equals 8, that's going to smear something. We can, what we can use is a matrix. So we're going to go into a matrix, and I want to do some math on a matrix. And if we scroll down to RREF, this is find the reduced echelon form of the matrix. And then I'm just going to put in the coefficients of each of these equations in brackets for the matrix, in brackets for the first row. And the first row is 1, 1, 0, 8. Close the first row, open the second row. 0, negative 2, 1, negative 11. Close the second row, open the third row, 9, 0, negative 2, 29. And then we hope that we plugged everything in correctly. And we get A is 3, B is 5, and C is negative 1. So we've found the reduced echelon form of this matrix. So that 1, 0, 0, 3 means 1A plus 0B plus 0C equals 3, and so on. I think MATLAB uses the same syntax. Incidentally, if you happen to be taking linear algebra over the summer, this is the operation that you perform. Notice that in linear algebra, I said this is the operation you perform because it's the only one you need. That's what's so awesome about linear algebra. You learn how to find the reduced echelon form of the matrix, and then you learn what that means in many contexts. So the other reason I point this out is that if you look up solving linear systems using matrices on the old YouTubes, on YouTube, they would have you go into the matrix and they would actually have you edit the matrix. If you're only going to use the matrix once, I don't want to enter the matrix in 2 times. I just want to put it into the face of the calculator. I don't want to go into the matrix editor and say, have to enter in the matrix. So I have to go into the matrix editor and edit my A matrix to be a 3 by 4 matrix. And then it's a 1, enter 0, enter 8. And then the next one is 0, enter 2, negative 2, enter 1, enter negative 11. 9, enter 0, enter negative 2, enter 29. Oops. 0, negative 2, enter 29, enter. Then I have to get out of the matrix editor, so quit, Then I have to go into matrix, and then I have to go over the math and call up my reduced echelon form. Then I have to go into the matrix menu again and bring in A and then hit enter. Just plug in the matrix right in the face of the calculator. Because I mean, if you're going to be doing this and missing out on all the cool row operations by hand, then that means you're going for speed. And so, you know, but then again, if you're truly going for speed in this original problem, just grab Wolfram Alpha and say, hey, Wolfram Alpha, what can you tell me about this rational function? And one of the things it'll tell you is the indefinite integral. All right. Tomorrow, we're going to look at some other of these variations on integrating rational functions. So make sure that you have this one in your pocket, because tomorrow I'm going to look at something like x squared minus 4x plus 13. I'll replace the x squared plus 9 with like x squared minus 4x plus 13. I'll give you a quadratic with complex zeros that has an x term. So we'll have to complete the square. We'll have to write things in vertex form. And we're going to see how that kind of mucks with things a little bit. So if you want a problem, a nice future problem to work on for tomorrow, the one I'm planning on asking has a denominator of x squared minus 4x plus 13, and the numerator is not going to be an x minus 2. The numerator is going to be x plus something that doesn't fit, x minus 5, x plus 5. So that's the one we're going to look at tomorrow. That's going to get at this complete the square business, because the denominator has complex zeros. And so we're still going to have arctangents and natural logarithms, but we're going to have to be clever about how we break apart the fraction. The cleverness is going to show up in this step, where it was easy to break apart 5x minus 1 over x squared plus 9. We're going to have to be more clever about how we break up x minus 5 over x squared minus 4x plus 13. All right, well, that's going to do it for today. I'll see you all on tomorrow. Sorry, I ran over a little bit. See y'all on tomorrow.
All right, see you, Professor.
Thanks for playing.